Thank you very much, Phil. That was a great discussion, and I'd love to hear some of the history. We're working on getting back to that ecology stuff. We'd like to see that as well. I now have the privilege to introduce our keynote speaker, David Mogk. I'm going to read this because there's a lot. Dave was a professor of geology, now emeritus, and former head of the Department of Earth Sciences at Montana State University in Bozeman. He specializes in the origin and evolution of the Precambrian crust in southwestern Montana, back to 4 billion years in age. His work also extends to mineral exploration for precious base and industrial minerals, as well as environmental remediation of mine sites, in addition to advocating for excellence in geoscience education. He has a very long list of awards, which I think I'll let him speak to if you want to. Dave earned his BS degree from the University of Michigan and MS and PhD from the University of Washington. So, without any further ado, I'll pass this over to Dave, and we'll get to the meat of the afternoon.
All right. Well, thank you for that very kind introduction. Thanks to all of you for coming out on this wonderful day to be out fishing or hiking, and thank you so much for being here. I started my PhD work at the University of Washington in Beartooth country in 1979. And over the last, I don't know, can't do the math, 45 years or so, I've had the opportunity to traverse just about every part of the Beartooth, but also Spanish Peak and the Beartooth and some of the other ranges. And what I'd like to do today is to share with you some of the amazing things that I've seen so that you can go out and see it for yourself. Now, before I get there, I do want to give a special note of thanks, first of all, to my former student, Jake Franklin, who invited me. I think he's on the board, perhaps. And then for Jim Bonini for the advertising, Matt Nancy Knight, Greg Tracy, and the whole staff at YBRA. There are so many people that make this place work as just a community asset, not only for Red Lodge, but for the larger geoscience community. Yeah. So before I start, I wanted to give a personal tribute to a friend of many people in this room, to Marv Kaufman. Marv was from Franklin to Marshall. He spent a good part of his career at the American Geosciences Institute. I don't know if he was director of the field camp, but he was certainly involved with YBRA for many years. For me, Marv was an important mentor in my life because he also did a stint at the National Science Foundation, and he encouraged me to apply and then ultimately to work as a program officer myself at NSF. And that was a major inflection point in my career. And so I just want to emphasize the importance of mentoring of the staff and faculty that run facilities like this. You never know when just a word of encouragement is going to make a huge difference in someone's life. And then I also want to just honor YBRA itself. Ginny Sisson from the, look, that's falling. Trying to not have any events here. Ginny Sisson from the University of Houston wrote a chapter in this book, which I've got a copy on the side here, if you would like to see, about the great legacy of YBRA. And I would just like to note that, again, we just heard, we can't spin an operation for 89 years. And Jenny wrote the article in 2009, over 2,000 students had attended the field camp here, which is an amazing contribution to geosciences. And in addition, they have supported numerous research programs, PhD projects, field conferences, and so on. And so my personal relationship with YBRA, again, goes back to 1979, because there was a field conference that was sponsored and run by Paul Miller and Joe Wooden. And it was on pre-Cambrian geology and geochemistry, and I got to meet the leaders of the field. Don Hunter came over from South Africa, Fred Barker from the U.S. Geological Survey. But it happened here. And this one-on-one interaction of getting to sit down and talk to people, sit around the fireplace, work with them on the outcrop, again, was immeasurably important to me, as I was just starting as a very green geoscientist. And then we came back, I was able to lead a national field conference for the National Association of Geoscience Teachers, where we brought 80 professors of metrology here. YBRA hosted this for a day as we went to the Stillwater Complex over the Beartooth Highway and beyond. And so this always has been an anchor or a safe haven for itinerant geologists passing through the country. So again, to all the YBR people, thank you so much. Okay, there we go. I do have to say a couple of acknowledgments. My specialty is on the very ancient rocks, the crystalline rocks up in the Beartooth. We'll talk about more than that. But this work was done with a consortium of folks, Paul Miller from the University of Florida, Darrell Henry at Louisiana State, and here we are, the Beartooth boys, many years later, a few pounds heavier, and Joe Wooden from the U.S. Geological Survey. And Phil, your comments about the USGS are spot on. We have really lost a lot. And I also have to say that over many years, I've been the beneficiary of many grants from the National Science Foundation that allowed us to do this work up in the Beartooth. And again, let's hope for more enlightened days when NSF will be fully funded and allow this research to continue. Okay, enough of that. Let's do some geology. Okay, there we go. Now, the title has the word geoheritage in it, and there's too many words up here, but what is this thing called geoheritage? Many of you are familiar with cultural heritage, like World UNESCO sites, maybe biodiversity, saving those special ecosystems that are unique in the world. But we have the same concept in geology regarding geoheritage sites. And geoheritage sites are sites that are, first and foremost, scientifically significant. Second of all, have an educational value. So here we are. But in addition, geoheritage sites also have cultural impact because where people live is intrinsically linked to the landscapes, the weather, the hydrology, and so on. And so geoheritage sites affect who we are and how we live on the Earth. And there's also aesthetic value. Just driving those busy highways, as you'll see. Cultural and also spiritual values as well. Now, I'm part of the International Union for Geosciences, and for the last number of years, we've been identifying 100 geosites in the world that have this special significance of being scientifically iconic, educational value, cultural value, and so on. And 2 sites in the Beartooth made the cut for the first 100 sites in the world. The Eastern Beartooth is one, and if you look at it in it, Stillwater Complex is the other. So I just want to impress on you how unique and wonderful this landscape is. Okay, now, I'm going to just ask, how many people actually had a geology course? Oh, a number of you have. Well, it's about half. Many of my audiences, that number is about a tenth. And so I just wanted to say just a few words about earth scientists' superpowers. How do geologists think and learn about the Earth? And I'm going to come back to this again and again. In the talk, I want to show you not only what we're seeing, but also how do we know? And so some of our superpowers are the ability to read the story of the Earth in the rocks themselves, in the rocks and the landscape. Passage of prologue. By looking at what happened in the ancient history of the Earth, we can understand what's happening today and perhaps predict in the future. Nature is a template for engineering. Nature had billions of years to get the experiments right. And we learned many lessons about how to harness energy and resources and so on from looking at the Earth. In my mind, I have to think from a scale of atoms to whole planets. So I have to be able to zoom across spatial scales that are orders of magnitude different. And the same thing with an understanding of deep time. The Earth's 4.6 billion years old, and so some concepts about time are things like frequency, duration, magnitude, recurrence intervals, residence time. And so some processes on Earth take billions and billions of years to happen. Others can happen catastrophically in just a flash. And so we have to be thinking across scales of time. We have an incomplete geologic record. We'll see good evidence of that at Beartooth Butte in just a few minutes. And what this means is we only have a few pieces of the puzzle, so we have to think using inference and also analogy. And so I'll be bouncing back and forth between contemporary examples and trying to use that as a way to understand what we see in the past. We have to think about complex systems. The first law of ecology, everything is connected to everything else. And we have these complicated feedback systems between the physical world, the living world, the chemical world, and humanity. And again, as a geoscientist, I have to integrate chemistry, physics, biology, maybe some engineering, and so on. So these are all mental gymnastics that have to be practiced. And that's one of the things that we do quite well here at Field Camp. And the tools that we use, for me, first and foremost, is field observations in nature. For me, it all starts in nature. What are the rocks? What is their distribution? What are they trying to tell me? I do a lot of sampling and bring the samples back for a variety of analyses and perhaps experiment. In other cases, we're increasingly doing modeling and computational approaches. And then there's theory. Don't worry about that spider web. There is meaning in there. But all of these things feed back on each other. They're like legs of a pyramid or legs of a table. Field work informs the analytical work feeds back into what we should be looking for in the field. So I'll be trying to show you how I interpret the landscape through these various prisms. There we go. Now, this is shameless self-promotion. Everything that I'm talking about today is all on a very extensive website. The URL is right down here. And I figured, well, I spend a lot of time driving back roads and hiking trails, and I can tell you there are some roads that you don't want to take your street vehicle on. And you won't know that unless, well, you can find out by trial and error, and it's probably not a good idea. So I try to put all this into one website where I've got logistical information, I've got field guides, road guides from Livingston to Columbus, Columbus to Red Lodge, up to Stillwater, over the Beartooth Highway to Cooke City, and then Cooke City to Gardner, and then back to Livingston. You can find information about trail guides from the U.S. Forest Service, where the campsites are, geologic history, maps, references, and so on. So if you want to follow up today, it's all there on that website. Now, let's take a look at this. Look at the Beartooth. We've got our big block uplift here, and it's just, so let's take a step back. The reason I came to Montana, and specifically the Beartooth, to do my dissertation is I had three criteria. One was very ancient rock. The second one was access to good fishing. The third one was high alpine scenery, and there actually was a fourth one, and that was access to hot springs. So these are very, very important motivators. But what we're going to do today, I decided that rather than go sequentially around spatially that's going to organize this temporally. We're going to start with the oldest rocks and work our way up. So we're going to start with evidence of 4 billion year rocks and work our way up to, well, June 13th, 2022. Remember what that was? Oh yeah. So, but in so doing, what we're going to do is we're going to spend some time on the highway to start with, going up Rock Creek, up the switchbacks here. Spend a little time at Long Lake. We'll go to Top of the World and Beartooth Butte. And I should note, thinking back to the Princeton legacy, a very famous geologist by the name of J. Wilson, who was the father of plate tectonics, did his dissertation here out of Princeton in 1936. And he defined the Beartooth in 4 blocks. We have the main Beartooth block here, which is all of these old crystalline rocks that I worked on. He defined the Stillwater block up here. We spent a little time there. I did my dissertation in the North Snowy block, and then we have the South Snowy block here, Gardner and Jardine, the rocks right around that area. We will take a look then at the stippled pattern here is the Absaroka Volcanics, huge volcanic field, about 50 million years old. And then we have a series of faults. We call these Laramide faults that we'll take a look at. And we have modern day faults in the alpine glaciation. So we'll start old and work our way young. Okay, now, what's the overall geologic setting of the Beartooth? Well, we refer to this area here, we call it the Wyoming province, because these are all rocks that are related. The very dark rocks on the map here are all instances of these very ancient crystalline rocks that are exposed on these high-angle Laramide faults. These being the oldest rocks in the continent, it turns out the continent grew laterally with age. It's surrounded by high-grade, I'll call them mobile belts, the Great Fault Tectonic Zone, the Cheyenne Belt, and the Cooke Orogeny here. These are much younger major structures that over time have accreted more and more material to the edges of the continent. So the continent's like an onion skin, with the oldest core right here. That's why they call it nuclear North America. And then younger and younger things being accreted to the edges through time. Another word for this is a craton. A craton is an ancient, stable, and thick mass of continental crust. Once the craton forms, it's very hard to destroy it. Gilliard said that trying to destroy a craton is trying to like flush ping pong balls down the toilet. Once you form it, it has high density, it stays high, and it's very hard to get rid of it. Now, for me, my main research questions are: how did continental crust form in the first place, which is what we'll see in the eastern Beartooth? How did continental crust evolve through time? And what was the mechanism? Do we see contemporary style plate tectonics working through all of geologic time, or has there been a change? So that has driven me for some 40 years. So when I talk about tectonic models, let me just quickly say we have a case of 2 large plates coming together where one gets subducted beneath the other. In a subduction zone like this, we call this a convergent margin. We have cases where 2 pieces of crust can collide against each other, and you kind of scrape off layer after layer and accrete it to the edge of the continent. We have continental collisions like the Himalayas. It's another possibility. And then in some cases, we could be like the East Coast, where not much is happening seismically, and we just have long-term subsidence and deposition of sediments. We call that a static margin. So I just put this slide here because I'll be referring to these types of environments a bit later. Okay, now, this is a geologic map of Montana. And let me just point out the Beartooth down here, and then the Madison Range, the Gravelly Range, the Tobacco Roots, the Ruby Range. These are all pieces of very ancient crust that have been faulted up relatively recently. So this is where you have to think carefully about time. The age of the rocks, when they actually formed, is very ancient, older than 2.8 billion years ago. The age of the mountain ranges are very young as a physiographic feature. They've been faulted up, and in some cases they continue to be faulted up over a great height. But anyway, the Beartooth are one of many of these fault block mountains in southwest Montana and then down into Wyoming. Now, what did the earliest Earth look like between 4 billion and 3.6 billion years? Well, we don't know. We don't have a rock record that goes back that far. There's only one or two places in the world that have rocks this old. The Gneiss up in British Columbia, and we have just found another slice in Labrador, I believe. But we don't really know. But we do know a couple of things. One is, very early in the Earth's history, there were more radioactive elements in the Earth at the time of formation, when the Earth accreted. And those radioactive elements gave off a lot of heat. But the heat didn't necessarily pass through all the crust. It was more channelized. And there is now evidence that very early in the history of the Earth, there was actually cold water on the surface of the Earth, and probably shallow sea. When crust is formed, it quite often is formed by melting the mantle many, many kilometers down, and the melt that comes up is a rock type called basalt, and it tends to form layered stacks, something like this. So think about the Hawaiian Islands as an example of this, where we have concentrated heat flow coming up in a plume, and it's constantly erupting, forming more and more basaltic lava flowing out laterally and building thicker and thicker continental crust. What we see then is this forms very large plateaus, and that got cut off a little, but here's the size of the Wyoming craton, and notice that it is the size of many of the current volcanic plateaus that are in the deep ocean. So we think that the very earliest crust was something like this, stacks and stacks of basalt. When this gets thick enough, it starts to melt. And when it melts, it produces small amounts of silica-rich melt that produce a mineral called zircon. So a large part of what I'm going to talk about here in just a minute is the story that we get from the zircon. So let's go to the Beartooth. This is a view on Cowering Plateau. So drive down to Limber Pine Campground, take the old haul road up to the top of Cowering Plateau. I don't think you can get there now. I think the bridge is washed out. I think it probably still washed out. For sure it is. Good fishing up there, but they'll just grow bitter. And what we see in this image here, this outcrop here, all the striped rocks, the layers that you see here, are the very ancient rocks that are the oldest in the Beartooth. And this is a combination of rocks that formed at the surface, things like quartzite and things that were shales that were then moved on to shift, and some old gneisses. And this is a screen or a pendant or an enclave inside of all this white rock looking out to Mount Rearguard here. These are all younger granitic rocks that are something like 2.8 billion. So think of this maybe like oatmeal, like a bowl of oatmeal that has some raisins floating in it. Raisins are the old thing, and then we've got all the oatmeal around it. And there are thousands and thousands of cubic kilometers of this younger granitic rock. This comes from his first map. I want to give tribute to the pioneers who worked out here. Hal James was with the U.S. Geological Survey, and he mapped the chromite deposits in this area in the 1940s for the war effort, World War II. And then in the 1950s and 1960s, Eric Poldevar and his students from Columbia worked out of YBRA, and there were, I think 6 or 8 dissertations that came out on their Beartooth project, and they did a lot of the mapping of these types of rocks in this area as well. So we've got enclaves of very ancient rocks in much younger granitic rocks. Again, just to honor the early workers, this didn't produce very well, but Clancy Casella published this from his dissertation in 1964. This is his map of the Line Creek Plateau. So when you head up over the switchbacks, you've got Line Creek and Wyoming Creek. But the important thing here is see these big folds that are in here. These, and you can see it in this more recent map from Meyer and others, big folds. These are rocks that formed at the surface of the Earth. They were sandstones metamorphosed to quartzite and shales that metamorphosed to schist. And these all were deformed and metamorphosed prior to intrusion of the granites that are out there. So we're going to look at that in a little more detail right now. So we have no rocks in this period from 4 to 3.6 billion years, but we do have zircons. And zircons are minerals that are very robust. They don't melt. They don't weather. And once you form a zircon, it's like the old De Beers thing about diamonds, zircons are forever. You really can't destroy a zircon. And we'll talk about the significance of that in just a second. But we get zircons out of these layers of quartzite here. Now, this is Quad Creek. So when you're going up the switchback, just before you get to the vista, there's a pullout where you can see this mix of stuff. And for those who are used to pancake, layer cake geology, this is not that. These rocks were tormented by metamorphism they were buried on the order of 30 kilometers depth. They were heated to 800 degrees. They were stretched out and deformed. And so all those processes happened deep in the middle crust. But you can see we've got some quartzite, we've got some iron formation, we've got some schist. And I will say, in terms of the history of geologic thought, this is one of the great controversies that actually was played out and resolved right here at Quad Creek. Eric Poldevar was of a school of thought that were the so-called granitizers. What this means is he thought that you could take a pile of sedimentary rock, pass hot or warm fluids through, and bring things like sodium and potassium into the rocks and transform them in a solid state to go from a sedimentary rock to a granite. And that theory held sway through the 50s and through the early 60s. Our school is that, no, what we're seeing are remnants of old sediments that were then intruded by magmas that were melted that came up and crystallized around these rocks. But anyway, the granite controversy played out, and it was from Poldevar to this Columbia-based thing here that did that early work. So, this is one of the how do we know slides. So when I throw around words like 4 billion or 3.6 billion, how do I know? Well, the Reader's Digest version is we have a lot of radioactive elements. The ones that I care about here are uranium, thorium. Uranium breaks down at a certain rate. It's radioactive, breaks down, gives off some heat, and forms daughter products that ultimately are lead. So basically uranium, radioactive, lead, stable. And if we know the decay constant, or the rate of decay, this is called the half-life, we can apply this to a fancy formula and calculate the age of the rock. So the great thing about zircons, there's my friend zircon right there, is once they form, they have a certain amount of uranium that gets into the crystal lattice at the time of crystallization. It acts as a closed vessel because you can't melt or weather the zircon. The uranium just churns away through time, breaks down, and forms more lead. And so what we do is we collect big bags of rocks, and I can't tell you how many tons of rocks I've carried out, crush them up, separate them. These zircons are about 50 microns in size. Put them in my fancy scanning electron microscope, and you can see this beautiful zoning that we see here. Every one of those zones is a different growth ring, a tree ring, in the zircon. And then we have a fancy mass spectrometer where we either shoot a laser beam or a particle beam, two different methods, the same result. And we can put the beam right in the center and on that zone and on that zone and get a time sequence. It's like a tape recorder of crystallization from the zircon. So when I put it in the mass spec, I get my uranium and lead isotopic ratios, put it into my fancy formula, and calculate the age. So that's how we do it. And from here to here is probably a full year's work. By the time you get the rocks out, you crush them, you separate them, you finally get some machine time. This is why we keep grad students around. Anyway, these are the results. So 2 types of zircon give us 2 different things. So on this side, this is an age spectrum of zircons that we collected from all the eastern Beartooth, Tellurine, Line Creek, Quad Creek. I think the number, 560 analyses. And every one of those spots calculates an age. And this is the ages that we get from the report site. And what this tells us is there was very ancient crust in the area dating back to 4 billion years. Oldest we dated here, I think quite correct, 4 billion, 3.96. But then we had a period of crust forming at 3.7 billion, another one at about 3.6 billion, and then a huge crust forming event at 3.3 to 3.2 billion years. So what this tells us is that whatever the source area was for the sand that made that quartzite, it was sampling crust from a lot of different provinces and mixing it all together. Okay? Then the other thing that we do is we do the same thing, only with gneisses, rocks that are crystalline rocks that have the composition of rock with granite. And this will give us the crystallization age, or the magmatic age. And again, we measure our uranium and lead isotopes plotted on this diagram. And what we see in the eastern Beartooth are ages that go from, let me get the right one here, 3.5 billion to about 3.25, 3.2 billion. By the way, billion is really a big number. Think of the national debt and then some. But and when you, I should have said this earlier, when you see the GA, that stands for giga-annum, billions of years. Then MA is mega-annum for millions of years. So anyway, so this just shows us that in the eastern Beartooth, we've got remnants of some of the oldest rocks in the world, either in the sediments or the oldest rock we see is 3.6 billion. Now, a few other words about the so-called old gray gneisses. This is at Lower Crab Creek. This is 1.5 miles up from the campground pull-off for Reno and Liver Pine campground. And this is why it's so difficult. We have layers of gray and white rocks in here. And the problem here is that the gray rock dated at 3.5 billion. The white rock dated as the age of all the enclosing rocks around it, the 2.8 billion. This is a 700 million year gap in time. That is longer in Earth history than we had hard part fossils in one outcrop. So the problem here, our challenge always has been that we have to take every rock, take it apart, because we can't tell just how much it is. And then on top of that, we have this big black mafic, basaltic dike coming through. We dated that at 2.5 billion. So these rocks have a long and glorious history. This is another example from Yankee Jim Canyon over on the Yellowstone Riverside. More granites. This was a mafic unit like this, but this got caught up in the deformation and got stretched like pulling taffy. Stretched apart at very high pressures and temperatures. So that's what we're dealing with. And that's what you'll see going up the switchbacks on the highway. Now, too much geochemistry here. There's only one point per slide here. So I fingerprint rock based on their chemical composition. We've done hundreds and hundreds of these analyses. I just want to make the point that for these very ancient rocks, we've got mostly rocks in blue, mostly rocks in red, and not a lot of rocks in the green here. We call that a bimodal association. So we've got black rocks, we got gray rocks. And that's what makes up most of the old stuff. This middle one, we call this a spider diagram. It's supposed to look like a profile of a spider. I don't know who made that name. But the fact that a couple of these elements are visibly depleted, it turns out that these are the elements that tend to partition into minerals that are removed and stay in the source area. And this is a fingerprint of subduction. So when you look at modern day subduction zones around the world, you will see exactly this pattern. So again, by inference, we're saying for these rocks that formed at 3.5 billion years, that they have the fingerprint of subduction. So this is getting to start to answer my question, when did plate tectonics start? The early stuff seemed to be a flume, the later stuff seemed to be related to subduction. And one other diagram, all of the red dots plotted in this field here, the VAG stands for volcanic arc granite. So think about modern day Cascade or the Andes. That type of environment where you have modern day subduction forming the snow cone volcanoes that we see on the West Coast. So we've got three lines of evidence here that says what we're seeing in the ancient rocks is very similar to what we're seeing in contemporary rocks. Now, after about 3.2 billion years, it looks like the tectonic engine shut off for about 200 million years. And the way that we know this is the youngest zircon that we see in the quartzites is 3 billion, and we know that they're intruded by 2.8 billion year rocks. So we bookend this, we bracket this. And in its period, this is when the quartzites and the shales were deposited. They must have been deposited in something that looks like the east coast of the United States today. It's just a very quiescent basin, the sediment coming out of the rivers, making it to the ocean, and depositing, as you can see here, sands and shales, something like this. And so those guys stayed at the surface of the earth until 2.8 billion. Now, at 2.8 billion, all hell broke loose. And a major orogenic event, orogeny means mountain building. And a major mountain building event started at about 2 billion years. And again, I wanted to juxtapose this picture looking out to Beartooth and up the fish hook around Rock Creek here. This topography and rock type matches almost perfectly with what we see in the Yosemite, in the Sierra Nevada Valley. Not just topography, but for me, the rock. Same composition, same structure. And so we're making the case that these rocks all formed in the same environment. The difference between these and the granites is these formed in about 30 or 40 million years, with a very, very tight age bracket between 2.82 and 2.79 billion years ago, and that's about how long an orogeny lasts in the modern day. So our argument is that by 2.8 billion years, full-fledged contemporary style plate tectonics is working, and then has continued to work through geologic time. Let's see what's going on. These are really complex rocks. So if you drive over the pass, over Lima, Kankakee area, and drop down to Long Lake, we've done a lot of very detailed sampling and mapping in that area. And I'll just point out that we've got gray rocks cut by white rocks, but in other places, the gray rocks cut the white rocks, and these are layered on a very fine scale. Parallel layers, we think that these are injections that are layer by layer injections. We see evidence of partial assimilation where one melt actually eats away and consumes some of the older rocks. We see evidence of magma mixing. So what this says to us is that numerous magmas were coming up at the same time and mixing at these mid-crustal levels. And I think the next one should be a cartoon of that. Oh, yeah, one other thing. So again, a couple of important points here. The first is, these are the first time we see rocks in large abundances of andesitic composition. That's roughly the composition of Mount St. Helens in modern day volcanic art. Again, volcanic art, again, the depletion of these elements. So we think that these are in art. And this just shows the range of ages from about 2.79 to about 2.82 that we get on multiple samples. So in this case, what we think is happening is that we're undergoing subduction in a convergent margin, but we're not just melting one thing, we're melting 5 or 6 different things simultaneously. So we're melting this black stuff here, we're melting the mantle, we're melting the lower crust, and all those magmas are coming up simultaneously and mixing in this zone here. And in aggregate, you get that with thousands of cubic kilometers of granite that you see across the Beartooth Mountains. Huge volume. Huge volume. Just think about the amount of energy that goes into melting, if you take sugar and you're going to caramelize something. A lot of energy that goes into that melting. We're melting cubic kilometers of granite in a huge portion of the work. Okay, what do we got next? Now, one thing that I do is collect rocks like this, and then I cut them very thin and look at them in a microscope. And we cut them thin enough so the light passes through the microscope, and we identify the different minerals. And these are just some examples of what we would see. But the important thing here is that by identifying the minerals, different minerals have different stabilities for pressure and temperature. And we can also see sequence of events. For example, this gray thing called opia is overgrown and surrounded by the green thing. So that means the orthopyrocene had been there first, and the green hornblende had grown to that. So we get time sequences. Okay? So again, this is another type of tape recorder to try to see what's going on. Now you're going to hate this next diagram. But the cool thing, look at the colors here to start with. Those are garnet. Everybody's has seen garnet in jewelry. Turns out that the compositions of minerals change as a function of pressure and temperature. So I can use my instruments in the lab, things like a scanning electron microscope or an instrument called electron microprobe. If you take a look here, the cores of the garnet have different calcium content than the rim. They have different manganese cores compared to the rims and so on. And we can use that because experimentally, some smart geochemist guys figured out how to calibrate this exchange of elements as a function of temperature and pressure. So I spent a large part of my career trying to do that, And we came up with this diagram here. This is pressure on this side and temperature on this side. And this dashed line shows the trajectory of the sequence of minerals that crystallized at different times during this mountain building event. I just want to point out that this goes up to about 8 kilobars is the same as about 25 or 30 kilometers buried. So we had to take those quartzite and shales that were deposited up on the surface and somehow figure out how to get them down to 25 or 30 kilometers down. So that's 15 to 20 miles. That's deep buried. And the only way to do that really is in a collision, where you have one continental mass riding up and over, if these are the sediments, continental mass riding up and over and pushing them down. Like that. So what this tells us is that we have very high pressures at one point, and then with time, basically the whole range lifted and decompressed, and it eventually cooled, and then finally down here. The fine detail is highly important. But if we have this type of, we call it a clockwise path, that in modern day environment is consistent with a collision. So again, we're seeing in the metamorphic rocks the same evidence as the igneous rocks, that all this is coming together because we had some kind of convergent margin collision. Now, one of the cool things about plate tectonics and about science indeed is theories are always changing, and since the first three boundaries were identified in plate tectonics, we come up with a variation on that theme, and that is the so-called accretion tectonics. And in this case, bits and pieces from somewhere else have come up along the coast here, the west coast, and plowed into North America. This Rangalia terrain up here started off at the equator, south of the equator. And it has migrated along these big faults, the San Andreas Fault and another one. Well, we think the same thing happened in the Beartooth. So I want to spend a little bit of time talking about the South Snowy Block and why we think that is exotic. It didn't start there, it came from somewhere else. And then my dissertation area is the North Snowy Block. So, first of all, let's go to Jardine. Okay? Many of you, everybody goes to Yellowstone to see the charismatic megafauna and the geothermal features. Many people don't realize the whole river margin of the park, from Slough Creek over to Gardner, are pre-Cambrian rocks. So I had a group of students at what's called our research experience for undergrad, sponsored by NSF, map this country, and these rocks are very different. First of all, they're layered rocks, sedimentary rocks that you see here. They're not highly deformed, like everything that I showed you before. They were not metamorphosed at those 30-kilometer depths and 800 degrees temperatures. We can still see primary structures. They're not wiped out. And so everything about these rocks seems different. And when we look at the zircons that came out of the quartzite here, it turns out that none of these ages match what we see in the Beartooth. So this whole block came from somewhere else. We don't know where. We don't have geographic coordinates going that far back. There are some rocks that are similar in the Black Hills. There are some rocks that are similar down at South Pass, at the south end of the Blue River. We're not sure. But nonetheless, all this says that, that these rocks, and they're deposited in submarine debris flows. We call them turbidity flows. And to get a turbidity flow, and the coarse stuff settles out, and finer and finer stuff. You get another turbidity current come out, and you do it again and again, and that's how these rocks form. Well, it turns out that these rocks had to have been deposited sometime between 3 billion years, which is about 2,900 million years, which is the youngest zircon that we see. But then it's cut by these plutonic rocks. This is another intrusive rock. That's the Hellwarren Hill. So if you go to Garnet Hill or the Hellwarren Creek Trail in Yellowstone, go north. That's the Hellwarren pluton. There's also the Crevice pluton. You've got a very good age date on that at 2800. So what this means is these rocks had to slide in from somewhere else between Beartooth time or before Beartooth granite, because this anchors it. This is a linchpin, if you will. So those rocks had to be in place before 2800, but from somewhere other than Beartooth. And we think that they came in on some of those big types of faults that I showed before. Now let's go to the North Snowy Block. So if you go to Livingston, about 15 miles south, go to Pine Creek Lake, that is my dissertation area. We see some major structures up there. So let me just show this. This is a marble unit. It comes around like this, and folds around like this, and folds around like this. This is the Glarus thrust in the Alps. Right there. Pretty darn similar, right? And then similarly, this is actually the thrust contact that I tried to outline in black there. These are more of the gneisses, and this is marble and quartzite that have been thrust over the top of that. These are horizontal tectonics. This is what happens in a collision belt. And so, again, these rocks came from somewhere else. They were faulted in from some long distance and faulted over those gneisses. So, again, we have an alpine-style collision in the North Snowy Block. We have a cratered terrain in the South Snowy Block. For me, that says plate tectonics are fully operational at this time. Now, we've got Ennis in the audience. Ennis, I think you gave this talk last year or 2 years ago? Yeah. So many of you are aware of the Stillwater. This would be a very quick overview. The Stillwater Complex is this amazing layered mafic ultramafic complex that resides just on the northern margin of the Beartooth, about 60 miles long. It has a very well-developed stratigraphy. I think this is from Steve McCallum, where we have an ultramafic or a crater-type zone. Just think of that as really not having physiogrammy, not having primary physiogrammy present down in this area. Then we have banded zone rocks that are varieties of gabbros, and you see that there's a very regular stratigraphy going up here. This has been dated very well at 2711, that's James, 2.7 billion years. And this is an important age marker because this shows none of the high-grade metamorphism or deformation we see in other places in Beartooth. So this is a late post-mountain building intrusion that came in along the north side of the Beartooth. You can see this amazing, this scale layering. You see this on the West Fork Road. Look at these huge crystals. We call those oikocrystals. Oiks are eggs. They look like eggs, the big shiny eggs in the outcrop. Anyway, really, really remarkable rock. And again, this was the source of a lot of work on geologic thought about how magma chambers work. Hess from Princeton and others thought that this was a case of crystal settling, gravitational settling. As crystals form and settle out and drop. And it was a very simple model. But then over time, we came to understand that there were multiple injections into the magma chamber. The most recent work says, well, it wasn't just injected into the top of the magma chamber. We had units injected in between previous layers. So you I'm looking at that because it's nasty stuff, right? Yeah. So we learned more and more, but this was one of the great natural labs trying to understand how magmas form and how they evolve in chambers right here at the Stillwater Complex. And then, again, our dependence on resources and geoheritage, and we'll just point out, this is mined during World War II, again, for the chrome deposits. This is Dr. Lake's camp up Mountain View. And here you can see the chrome seam that they were after. Not very big. That rock camber is only about 18 inches. And so, a lot of work for not a lot of value, I'd say. And then, of course, the modern day Stillwater mine that is the only platinum palladium mine in the country. And I think the numbers are still about 10%. Is that right? We produce 10% of the nation's platinum and palladium? About 10%?
Oh, 7% worldwide.
7%.
7%.
Yeah. Yeah. So, anyway, so a great legacy of mining up here in this area. Well, I think I'll just pass that. This is just kind of a summary of the pre-Cambrian. I mentioned the first slides were about forming this thick layer of basaltic flows, and then a little bit of partial melting to get our early zircons. Give it a little more time, we start subduction, we start bringing some more stuff up from the mantle, and we produce all of our old gray gneisses. This stuff made it to the surface and eroded off into a basin by about 3 billion years. And then that stuff got sent back down the tubes again in a major mountain building event, forming all of the new pink granite and then metamorphosing into forming the older rock. So that's kind of our model. Okay, now we'll leave the Precambrian and we'll go up in time. I want to introduce this concept of an unconformity because this is one of the most profound leaps in reasoning about natural science ever done. Hutton theorized, well, Hutton produced the idea of an unconformity when he realized, these are original sketches from Lyell's book in 1862, when he realized that sedimentary rocks are deposited horizontally to start, but here we've got a bunch of sedimentary rocks that are not only tilted upwards, but folded. And you can see this in Hutton's early sketches. And then there's an abrupt break, and then more sediments are laid on top. This opened up the idea that there could indeed be deep time. And what Hutton realized is there was a big jump in time that's missing from the folded rocks here to the later rocks deposited on top. Now, those unconformities can be big or small, and we're going to talk about the great unconformity. But the importance of this, among other things, is it gave Darwin license to formulate origins of the species due to natural selection, because now he had enough time for mutations and natural selection to work. Before that time, we had before the 1850s, 1860s, we had no idea what the age of the earth was. And so, but we see this in the Beartooth, right here, in a couple places. So now we're driving over the top. We're about a quarter mile east of top of the world, a little service station up on top. And this is really a profound unconformity because here's our 2.8 billion year granite that we saw previously. They've been eroded off, and then these light-colored rocks here are the flathead sandstone that was deposited about 560 or 540 million years ago. So you can literally step across about 2.3 billion years worth of history in one jump. It's amazing. It's amazing. And then tanks and how done. Now, so what was happening in the world at this time? Well, over time, there was gradual uplift. The crystalline rocks made it to the surface and were eroded off. And then in the Cambrian, shallow seas encroached across the continent and deposited the flathead sandstone, and in the Devonian, a bunch of shales, and by the Mississippian time, we got the big thick limestone. So the Madison limestone produced the big palisades out there. So just shallow seas coming back and forth across the continent, depositing, and that's what we see at Beartooth Butte here. So, go to the next slide. This was not a setup. You recognize this, Bill? That's from Dorf's work, where they finally published in 34, 35. Everything that Bill talked about, this little Beartooth Butte formation here, they did indeed interpret that as river and stream deposits. And what we're seeing, this is from the original publication, these are the original plant fossils, and there are the snouts and the various parts. Oldest terrestrial plant and oldest fish fossils in the world showing up right here on Beartooth Butte. Don't collect up there. You need a permit. But again, a great leap forward in scientific thinking. Okay, now, why do we have the mountain range? Well, I just told you we were a flat coastal plain with sands and limestones being deposited. Somewhere around 100 million years ago, it varies place to place, and there are different estimates, whether it's 100 million or 80 million, 20 million years among friends, but somewhere about 100 million years ago, we started having rock uplift. And these are, so the so-called Laramide faults are deep-seated faults. You go down 20 kilometers, sometimes a bit deeper. They angle up steeply to the surface. They bring our lovely deep-seated crystalline ancient rocks up to the surface of these faults. And they rise up and over the younger rocks, and that's what you're seeing in the Madison limestone palisade all the way along the edge of the ridge here. You got to be a little careful because I'm not fully a structural geologist, and this worked on the triangle zone up there, so I got to be careful. But you know, there we have basically you've got flat-lying sediments. The crystalline rocks come up, tilt like the edge of the saucer, tilt the rocks right up on end to near vertical, sometimes even overturned. Okay, riding up and over. And this is what we see in all the black ranges that we see here: Beartooth, Bighorn, Wind Rivers, Teton, Madison Range, Woody Range, Quebec Range. Anything that's Archean core or crystalline rocks at the core of the range really has these rock faults that we see here. Yeah, so this is the early work by Booth, Weiss, and YBRA, 1961. I really do want to honor this early work because this really was amazing work. Because they don't have the satellite imagery that we have now. You know, they did this, you know, Booth and Burrow, and this was the original map published in this publication. You can see the fault lining the Beartooth fault here along the front, coming down to the front corner here. Other major structures out here, the Nibor, Lineament, and this one I care about. And then they drew these wonderful cross sections that you can see here. Again, here's the Carsport Fault, here's the Indian Hill, the Beartooth Fault here. So you can see this popping up like a cork. Squeeze from the side, popping up like a cork. And yeah, so we see it in the Flatirons here on this side of the range. We also see it over in Paradise Valley on the west side. These again are these, let's see, these ages here are Triassic through Cretaceous, but tilted right up on end in the vertical aspect along the Spanish Creek Gardner Fault, and this is kind of the southbound fault of the Beartooth. So we see it on the north, we see it on the south. And then I did want to give credit to Jake Zachary. He's not here today. He's one of my students on his master's thesis. He works on faults related to the Stillwater Complex. He's teaching at Eastern now. But he and his students are working on this wonderful rock, what we call the Laramide Porphyry. Look at these big feldspar crystals that you see here. And a lot of times these are doubly terminated, perfectly formed crystals. If you go up there, up on top of the Line Creek Plateau, this is his recent mapping. Line Creek is way through here. you can pick up pocketfuls of it. I used to do this for my mineralogy class, and it's just beautifully doubly terminated twin crystals that are these feldspars. These are important because they're an age marker. These have been dated, I forget exactly the age, but about 50 million. But cobbles of these are being found out in the basin adjacent in the frontier formation. So we have a way to pin the age of uplift, erosion, and then deposition in the basin that are adjacent. So I'm sorry, Jake's not here to say a word about that, but thinking that way. Let me get oriented here. Yeah, so here's the Bighorn Basin. Here's the Beartooth. And we do have a number of basins, Bighorn Basin, the Crazy Mountain Basin around. I won't say anything about that soft rock stuff that I stay away from. But for field camp here, they do a lot of good work out here, a lot of oil and gas exploration work out here. So I'm just going to quickly pass through that before I explain myself. Now, also, in about 50 million years, we have a massive outpouring of volcanic rock, the Absaroka Volcanics. This is, I think, the largest of all of the Eocene volcanic sequences that include the Challis volcanics in Idaho, the Cambrian volcanics up in Washington. Just a huge outpouring of volcanic rocks. And you can see them here, pilot and index. My former colleague, now cast Bob Chadwick, did a lot of the good original mapping. And starting up at, here's Livingston, starting up here at Bozeman, the volcanic rocks are extended at the surface from up here all the way across the northeast corner of Yellowstone Park, and then all the way down to Toki Pass. Here's Du Bois, just huge, massive amounts, 10,000 feet of this stuff. Bob identified an eastern sodium-rich variety of volcanics and an eastern potassium-rich variety. But anyway, these are eruptions that would be very similar to Mount St. Helens. We'll see that in just a second. Along this northwest trend. These are deposited directly on this layer here. Bighorn dolomite is a Devonian sedimentary rock. We'll come back to that in just a minute. And then we see this is just a volcanic density for itself. But what caused this whole thing is, we believe, subduction of what's called the Farallon plate, an oceanic plate that dips beneath the North American continent. There's something called flat slab subduction. It's at a very low angle. It releases fluids up into the rock above, and those fluids flux the rock above that induces melting. And so we get two things. We get volcanoes, and we think that this also is a driving force for the Laramide fault. It's squeezing these massive plates coming together. Laramide faults going up, partial melting, making volcanoes at about the same time. So there's a couple of really special things about the Absaroka Volcanics. Let's start here with the petrified forest. We see these in Sesame Ridge, the Yellowstone National Park. You also see them at Heart Basin on the Paradise Valley side. George, who is from Princeton, is that right? He's one of the YBRA old-time faculty. Do you remember? Yeah. Anyway, so he described these in great. So this covers an area of about 64 square kilometers, about 366 meters thick of the volcanic rock. And these are tree trunks that are in light position. And they're silicified. And there's petrified wood all through here. Well, this was Mount St. Helens right after the 1980 eruption. It's pretty similar, doesn't it? So we think the same process. And basically what happens here is the volcanic ash is still hot. You get groundwater percolating through. It's a bit hot. It dissolves in silica and it goes into these places. And in my scanning electron microscope, I have actually seen cell structure from this type of petrified wood. The individual cell structures are still preserved on that final scale. But the thing that's amazing is that there were 27 successive forests identified at Specimen Ridge. So you had grow forest, knock it down, pour some soil, grow forest, knock it down, and do that 27 times. And in addition, they found over 80 species of trees and shrubs cataloged in these various volcanic deposits. Pretty special, pretty amazing. Other special things, this will really blow your mind. This is the Heart Mountain Detachment. Okay? So, we're coming back to this picture here. Here's all our volcanic rocks on top of this gently sloping bighorn dolomite layer here. This is the world's largest landslide. If you take a look here, here's Cooke City. Cody's down here. This whole block slid as much as 40 miles to the east. Now, there is controversy about this, and on the website, it goes back and forth about this. There's a question about whether this all slid as one big block, or whether it slid as a series of successive blocks. There is some question about how was it triggered by a volcanic explosion or a seismic event. But what seems to have happened is somehow a fluidized layer of gas got underneath that sliding plate. You played air hockey? Kind of like air hockey. And once that plate got fluidized, it slid from Cooke City. And if you know where Heart Mountain is, the other side of Cody, that's the upper plate. That's probably the upper plate of this whole Heart Mountain Detachment. It's amazing. Now, this guy Craddock, I don't fully believe this, but he calculated the rate of displacement as being 126 to 340 meters per second. Can you imagine standing on this ridge, looking out and watching that mountain move at 340 meters per second? And if you calculate the whole distance, that comes out to 600 miles an hour. Now, that's one estimate. This guy, Losh, I'm sorry. We did other calculations. It came out at about 90 miles per hour. But still, you're moving a mountain at 90 miles an hour, 40 miles. So, there are strange things in the universe ratio. And this is one of them. Gravity tectonics, initially described as Bucher in the 1930s, and still an item of great controversy and discussion. Then we have the Cooke City Mining District, and many of you, I'm sure, have been around following the whole controversy of Crown Butte and so on. Minerals were discovered in the area as early as 1869. Lovering from the U.S. Geological Survey described it in 1929 in a series of papers. And it's not just Cooke City, we also have the Immigrant District, the Independence District, the Sunlight District, and so on. The McLaren pit was opened from 33 to 53, and it produced over 300,000 metric tons of ore with 6 grams per ton of gold. We now mine gold at less than a tenth of an ounce per ton. Okay, so this was a rich deposit. It had quite a bit of silver and copper. In 89 to 96, Miranda Crown Butte Mines came in, and they drilled, and they discovered another 7.9 million metric tons of ore at 0.26 ounces per ton of gold, and silver, copper, 2 million ounces of gold sitting under Crown Butte right now. Okay. But Crown Butte flows into Fisher Creek, flows into Icicle Creek, down the Lamar, into the Yellowstone. But huge controversy about mining in high alpine areas, and having all these heavy metals going down into the Yellowstone. The bottom line is the U.S. removed Carter from Clinton. I'm trying to remember, I think it's Clinton. Removed Crown Butte from exploration, bought the mineral rights for $65 million, committed to $22 million in environmental cleanup, traded for land out away. So those 2 million ounces of gold are still there, but this is now closed to mineral exploration. So it's a great place to visit. You'll see a lot of historical mine dumps. Don't take your street vehicle. It's one of those places, don't take your street vehicle. Okay, so going up in time, the last couple of things I just mentioned, the Earth is still rocking or rolling. If you go up Paradise Valley, this is the rest stop on Highway 89. You look across these white cliffs that you see here. Those are kind of chalky, silty cliffs. They're about 11 or 12 million years old. And it turns out that those were lake bed deposits. So there were intermontane lakes, very dry lakes, that were seasonally occupied. You can find camel in the first teeth in here, and tortoises, and rodents. So, this is an important point of kind of evolution of ecosystems and habitat. And then if you go just at Jardine, Deckard Flat, and then if you go to Heifer Mesa right here on top, and you look at images, these are basalts that are basalt flows that are about 2 million there. And what's interesting about this is the same age, exactly the same age as the Huckleberry Ridge Tuff in Yellowstone, the first major eruptive cycle in Yellowstone. And so there is some speculation that the ages of these basalts may have been kind of the basalts that were intruded at depth that may have triggered the Huckleberry Ridge Tuff. We don't know, it's speculative. But nonetheless, you will see these flat plateaus of volcanic flows just outside of Jardine, and again at Evergreen and Heifer Mesa. And then finally, I'm way out of my league here. I'll just say that much of this work is Ken Pierce from the U.S. Geological Survey, who was in Bozeman with the USGS, Berkshire passed away in the last year. But Yellowstone itself had an ice cap that was about a mile thick. Okay? And with that much weight of ice, it forced glaciers to flow out the major drainages. So when you go out to Madison, when you go out to Snake, when you go out to Yellowstone, ice flows out away from the ice cap itself in the Yellowstone Plateau and out the major drainages. Now today, we see vestiges of those glacial landforms that were called neoglacial deposits. We see a rat, we see surf, we see farms, and so on. We've got the beautiful U-shaped valley of Rock Creek, we see hanging valleys. And so this is all evidence that glaciers cover all of this country. And then we see it. Here's another thing that falls in the category of absolutely amazing. This is one of Ken's early works. So we had this ice flow out off the Yellowstone Plateau, out the Yellowstone Valley. This ice flow made it halfway up Paradise Valley to the town of Keynote. So that would have been like 30 miles or so north of the park, just squeezing out right from Houston. There's one thing that Ken recognized, though, is that there were periodic ice dams that would breach. They form a lake, they breach, and you have a flood. And what he recognized is that these deposits that you see here are basically ripple marks that are as much as 500 meters across, 20 meters high, and spaced at about 15 meters. So if you can picture just in a river today, you see little ripple marks. These are tens of meter ripple marks. Here's one that you see. This is a ripple mark with boulders that are marking the crest of the ripple. And so we have these big catastrophic events that are happening periodically as the ice dams are breached, and we did this repeatedly. So great insight from Ken Pierce. And this is an aerial view looking at Paradise Valley again. Chico Hot Springs here along the margins. These are all channels, and those are ice marginal channel deposits. There's some kettles out there. That's dead ice topography. As the glaciers retreated, they leave behind chunks of ice, and sediments would fill around that. And then when the ice finally melted, we left with little kettles. There's some great swimming holes out there. So there's a great glacial story up in the high country, but also down in the lowlands as well. Now, I said that the rocks are ancient, but the mountains are young. The mountains are still going up. Not only do we have the Laramide Fault, I didn't tell you what the throw of the Laramide faults are. If you take the unconformity of Beartooth Butte and find the equivalent unconformity out in the basin, that's on the order of 20 kilometers, 10 or 12 miles. That's how much uplift that we had to have happen. But we're still going. And so these green images are LiDAR. This is a form of remote sensing that allows you to see through the vegetative cover and just see the landscape. And if I just trace this right here, that's an active fault in Paradise Valley that's cutting that alluvial band. That's still moving. And we can see it here as well. And the other thing is that we think that this is the same type of fault that created the same magnitude earthquake that Hebden Lake in 1959. If you know the big earthquake slide and fault story over at Hebden Lake in 1959. This is almost identical to that. And if you look at the LiDAR imaging on Beartooth Mountains, just up Yankee Jim Canyon, these are landslide scars. And this stuff all came down and dammed Yankee Jim Canyon. So we think that there was the same thing in Slide Lake going up Yankee Jim Canyon. And indeed, if you go up towards Gardner, you will see lake sand deposited on the side of the road. So as far back as Gardner, you see the lake deposits associated with these landslides. And the last couple of slides, if you have enjoyed blue ribbon trout fishing in Spring Creek, or if you enjoy soaking in hot springs, you owe it to the local geology. Okay? All comes down to geology. Spring creeks are here because the Cooke Creek Fault came up and formed an aquiclude. So we've got a hydraulic gradient coming down Paradise Valley, this is fault. And those waters come welling up with a constant temperature, high nutrient value, and that's how you grow those big sapling rows and mountains. Okay? And then the hot springs are adjacent to major faults. You get some hot water flowing down the fault zone, heating up, and you got Chico Hot Springs and the Yellowstone Hot Springs. So think geology for that. And then this is something too near and dear to all of you. June 13, 2022, this is in town, you all know that. And then wiping out the Gardner and the Lamar, log jams on the Yellowstone. And let me just quote YBRA. Civilization exists by geologic consent, subject to change. Some topical issues, just to close. This is just a wonderful, wonderful piece of country that I think we all love and want to preserve. But it does raise some interesting ethical questions about preservation of wilderness versus conservation, use of resources. That's Stillwater Mountains, well, we'll talk about that in a second. What's the right balance? Is the concept of wilderness elitist and exclusive, or essential for the health of ecosystem as a refuge? Think of people who are disabled who don't have access to all the great things that have any nothing. You know? So it's not an either or. There's some interesting questions there. Can we responsibly mine in sensitive areas? And we have many historic mines. Stillwater, Jardine was a big gold mine just a mile north of the North boundary. Cooke City, we just saw. There are certainly important economic contributions. We need the resources, good paying jobs, tax base. On the other hand, what are the environmental impacts and consequences? These are questions that we need to talk about and need to address. Impact of climate change, everything from diminished snowpack, water resources, driving over these roads that hardly the flow right now. Right? So there's water resources, warming water that impacts viability of fish, forest mortality, loss of habitat. Still talks about the loss of whitebark pine and the important there, food, nutrition. energy production, water for dams, for hydroelectric, commerce downstream for large traffic, is all connected. And what happens up here is the climate change necessarily impacts the whole system. And I think this may be, oh yeah, I wanted to close with this because I did want to remember the people who lived here. Yellowstone has always been a crossroads for Native people. And I won't read all of the tribes and nations that live here. I would like to say just a word about the Crows, being perhaps the closest to it. The Fort Laramide Treaty of 1851 needed 30 million acres for the Crows. In 1868, that was reduced, the second Fort Laramide Treaty, that was reduced to 8 million acres. As homesteading continued to think about what was happening in 1868, we had the big gold rushes. We had Bannock, Virginia City, Cooke City, immigrants. In 1872, indigenous people were removed from what was Yellowstone National Park because of the growing geotourism and feeling the need to decrease the sense of danger. In the 1950s, Big Horn Canyon was ceded to accommodate Yellowtail Dam. And now the Crow Reservation outlined here is down to 2.2 million. So let's just be a little respectful for the people who live here. And finally, next slide. Last thought from Teddy Roosevelt: here is your country. Cherish these natural wonders. Cherish the natural resources. Cherish the history and romance of the sacred heritage for your children and your children's children. Do not let selfish men or greedy interests in your country of its beauty, its riches, or its romance. So, get out and enjoy this magnificent country. Thank you. And I'll take any questions. I don't know how much time we have. The matter is great, but and I'm hanging around for the afternoon. So, any questions? Way in the back.
I have a question about when you're driving along the Chief Joseph Highway. There's like a wall that runs along that whole side there. You know,
Oh, a wall at Chief Joseph Highway?
Yeah, along there there's a layer that looks like solid, like you couldn't go up and under.
Yeah, I think you're talking about Cathedral Peak.
There's a horizontal wall and almost the entire length of the highway.
On the north side?
Along the north side.
Yeah, I'd have to see on the map, I'm sorry. But if you know the local geology,
Well, maybe if I'm
Thank you, Dave. That was a great talk. We covered 4 million years. Everyone very much. You can indulge us just 2 minutes before we venture out on the deck and enjoy some snacks. I'd like to introduce Denise Lord. She's a longtime YBRA supporter, former board member. She has a couple of words about our speaker, Phil Roberts.
Hello, thank you for coming today. These are always exciting events, and we always learn some new and fun information. But what I want to do now is, I want to talk about one of my favorite YBRA people. And he's sitting in that chair right over there. And I want to see if I can go, because I want him to hear me very well. You're going to sit there and be the wonderful guy you always are. Bill, you had talked about how YBRA was a very big part of your life. And I have been working on the YBRA archives this last year. And let me tell you, you are a big part of YBRA. your memories of YBRA. YBRA is full of memories of you. Going to the archives, you have articles, you have pictures, you have magazines, things that you've done, the classes that you created will be a part of YBRA history forever. The walls that are in here have stories that you've told, and I wonder if there's a chance, because Phil is moving permanently to New Mexico, and he's going to get busy down there, and he might not have the opportunity to come back to create more memories to put into this place. Just wondering if you could do one more cowboy poetry, maybe Cowboy Time.
Well, one of my hobbies since the late 80s has been cowboy poetry. Because when I was a kid, all I wanted to do was be a cowboy. And it's a pretty good thing that I didn't end up that way, because it wouldn't work. But you have a lot of trouble when you hear a talk like that. So many billion years ago and million years ago, and it just gets overwhelming. So maybe this will help. This was written by Baxter Black, who was one of my roommates in college. He was in vet school and I was in graduate school. What a hoot he was. If Genesis was right on track concerning Adam's first, and 7 days was all it took to build the planet Earth, then where does carbon dating fit? All those dinosaurs, plus all that other ancient stuff that happened on the shore. Now, I believe in scientists. They're not just lunatics, but I believe in Genesis, and that leaves me in a fix. The answer finally came to me while making up this rhyme. God made the earth in 7 days, but that was cowboy time. Did you ever call a shoer to set aside your day? Scrutinize your calendar and say Tuesday will be okay. The big day comes, you take off work unless it's never seen. You call him back and he said, well, which Tuesday did you mean? Did you ever place an order to have a saddle made with A43 and padded seat and silver hand inlaid? As the decades pass, all you can do is sit around and eat. So by the time it finally comes, you've had your own seat. In a while, a couple of days, not long or right away, should not be taken literally in cowboy jokes. But like I said, the precedent was set so long ago, the angels had to learn themselves what all good cowboys know. They worried that if they didn't work to keep the schedule tight, the earth would not be finished by the deadline Sunday night. So he paid the angels to relax and said, I'll get it done in 7 days, however long it takes. A guy wrote by the name of Arizona poet wrote this. Kind of a sad poem. We were gathered around his coffin, eyes welled full up with tears. We had come to lower the last remains of a friend of 30 years. The preacher looked in my direction, asked me to say a prayer, to give the benediction while we were standing there. Well, I never thought much about praying, never talked to God out loud, especially here at a funeral, in the presence of a crowd. But that was my friend there in that box that we had come to lay to rest. And if it were him in my place, he'd try to do his best. Old Jake never was a gambler. He never cheated on a friend. He liked his smokes and whiskey, but only now and then. and he never used much cuss words, except at branded in the spring, or building fence, or breaking broncs, or doing almost anything. Tell you the truth, Lord, Jake was lazy. He didn't have much sense. He was always borrowing money from me to keep up his expense, which was women, Lord, down at the hotel. Well, he was down there every night. And you know, Lord, he still owes me $50. And you know that ain't right. So, Lord, Jake wasn't much of a friend, near as I can tell. So, Lord, just forget this prayer and let him go to hell.
Thank you, Dr. Phil Robertson, for everything you have given to YBRA.
Hey, we have food out on the deck if it hasn't been blown away yet. And so enjoy yourselves, spend some time. There's good stuff on the walls here in the lodge. Hopefully we won't get a downpour.
I think it's too late.
All right, settle